Okay, so we're going to start off this first video about parent function transformation. So we're going to learn how to graph offspring graphs. So basically you now know that we have several parent functions, and we're going to learn how to take these parent function graphs and move them left and right and up and down on the coordinate plane, and these new graphs are called offspring. And so I've got some basic notes here that I actually want you to push pause on the video and write down these basic notes, and we're going to use them to learn how to graph new functions. So I used the quadratic for my first example as a basic note problem here. And notice in this quadratic problem, first of all, I know it's quadratic because it's squaring. So this is my parent function is being squared. But when the parent function has numbers as a, h, and k, these numbers do something to the parent graph. So for example, if there's a number there besides 1, okay, it tells us a whole lot more about whether the graph's going to be skinny or wide. But right now we're just going to talk about the concavity. So A tells the concavity of the graph, which means if A is greater than 0, or if A is positive, then this squaring function, this quadratic function, is going to have concave up, so it's going to be a smiley face. If A is less than 0 or negative, then this graph is going to be concave down, or a sad face. If there's a number inside the parentheses, then this thing inside actually lies to you. So H is what this is called. H describes the horizontal shift. H tells you how to move left or how to move right. And so if H is a negative number, the graph actually shifts right, which is why we say the graph lies to you. If H is positive, the graph shifts left. The K, the number on the outside, doesn't lie to you. It does exactly what it says. And the K describes the vertical shift. So if K is a positive number, the graph shifts up. If K is a negative number, the graph shifts down. So now that we have talked about the basic notes, we're actually going to do a couple examples together. So I'm going to start off with an absolute value function. So here is the first problem that I want us to actually work on together. And I'm going to make it larger a little bit here. And we're going to work on this first function, the f of x equals the absolute value of x minus 2 and then plus a 3. And so using our notes, we want to look at the a value. Well, there's nothing outside of my absolute value, so we're going to say there's an understood positive 1 here, which means my absolute value graph is going to be a V. It's going to be the shape of a V. It's going to be concave up because that 1 is a positive number. But we also know by looking inside that I have an H value. And this H value is a negative 2, which actually means that we're going to take this vertex and go the opposite. So negative 2 makes me think about going left, but because it's inside, we want to do the opposite. We actually want to go positive 2. So our vertex was the very first point we always want to try and find. Our vertex x value is going to be a positive 2. The 3 on the outside is my k value, and k tells me the truth, so the k value is going to stay the same. It's a positive 3. That means that we're going to take this graph, the parent function, and we're going to shift it right 2 and up 3. So right 2, up 3, and this is going to be the very first point of my absolute value function graph, the very first point. Okay, so we're now going to find points around that vertex. So I want to look for numbers around this x that I can start plugging in. So numbers around 2. So when I think about numbers around 2, I want to think about 1 and 0, 3 and 4. Okay, so I want to work on plugging those in. 1 and 0, 3 and 4. So over here we're going to show some work. Okay, so 1, 0, 3 and 4. So I'm going to put 2, 3 right here in the middle. It's going to be where my vertex is. 2, didn't show any work, so I'm going to get 3. So my order pair was 2, 3. But I also want to go the other way and show my work for 1, 0, 3 and 4. So if I start with 0, then that means I'm going to take my absolute value, plug in a 0 in place of my x, and show some work here. So 0 minus 2, well, that means I have a negative 2 inside the absolute value. But we know the absolute value of a negative number turns to a positive. So what I really have is a positive 2 plus 3, which ends up giving me a 5. So this order pair becomes x was 0, my y value is 5. Well, then I want to go back in and plug in the 1, and I'll change color so it's easy to see here. I want to plug in a 1 in my problem. So I take the absolute value of 1 minus 2 and then plus 3. Well, 1 minus 2 is a negative 1 plus 3. Absolute value of a negative 1 is a positive 1 plus 3, which gives me a 4, which means my order pair for this one is 1, 4. Do the other side, same way. Plugging in my 3. I'll leave more room next time. Get the absolute value of 3 minus 2 and then plus 3. Well, 3 minus 2 is 1. Absolute value of positive 1 stays positive. So 1 plus 3, I get a 4 again. So this order pair, 3, 4. Then I'll go back with my 4. And I'll plug in a 4 in my function. Same math. 4 minus 2. So inside the absolute value, I got a 2. Absolute value of positive 2 stays a 2. And 2 plus 3 gives me a 5. So this order pair is 4, 5. So if I go plot these points, 0, 5, 0 on the x-axis, 5 on my y-axis puts me there, 1, 4 puts me here. I've already got my 2, 3. And I want my 3, 4 puts me here. And then my 4, 5 puts me here. And if I graph these in the shape of a V, there's my concave up V function. You'll notice that this took the parent function, which is originally at the origin, looks just like this. So we took this orange parent function and did exactly what we said we were going to do right here, which was pick up this vertex. We shifted it 2 to the right and 3 up, and this red function is my new function. This is my offspring graph. Okay, so that's one example. I'm going to stop this video here, and I'll start a second video to show you a couple more examples.